Okay, so today we're going to finish out neural networks. This is actually the last curriculum study group that we have, which is crazy to think about, but not to fret. Throughout capstone, there's going to be a bunch of other study groups. I'll talk about some things that are either extensions of what we've learned, or I guess depending on what your capstones end up being about, I can come up with a bunch of other study groups that will support the topics that you're working on. So just to wrap up today, some loose ends from neural networks that we haven't yet talked about. 4 main things. First, using pre-trained networks, and I'll go into that later, but basically very similar to what we were talking about with word embeddings. There exists a bunch of pre-trained networks that have already been trained on mass amounts of data that can help, help alleviate some of the training that is needed to be done on your own neural network. Next, I'm going to talk about doing grid search for neural networks, which is also possible. I'll talk about saving your neural network because you don't want to have to keep retraining your model every time. So for example, with the machine learning models we did in Mod 3, they don't take super long to run. But as you know, you don't likely want to run your grid search over and over again. So I'll talk about how you can save your model. And then finally, we're going to talk about recurrent neural networks on a very, very high level. I have a presentation that I have just uploaded onto your repo that goes through recurrent neural networks, but I'm going to talk about it at a very high level. Admittedly, I don't have too much of my own experience doing recurrent neural networks. So it's just a lot of theory, and I have linked to a bunch of examples in case any of you want to implement your own recurrent neural networks for time series data. All right, to start, let's talk about pre-trained networks. So a pre-trained network, and specifically for CNNs, they're called a convolutional base. This, by the way, there are, I think, a couple or 1 or 2 labs in the appendix on pre-trained networks. So just in case you want more information on that, that exists there. So basically, a pre-trained network is a bunch of layers that has already been trained on typically very general data. So I think it's easier to talk about it in terms of images. For images, these layers have already learned very general things. So maybe they have a bunch of neurons that are focused on patterns. Maybe a bunch of their neurons have already focused on textures and colors, such that when you feed in your training data, those features are immediately detected. And the only part that really has to be trained is, maybe you're inputting images for 3 different classes. They're just tuning where your images go according to those 3 classes. So that part of using pre-trained network is called feature extraction. It's just feeding your own images into networks that have already been trained to detect certain things. We're actually going to go through an example of this, but typically you add your own final layers to train the network to classify or regress based on your own problem. So this component is known as the fine-tuning part. So utilizing pre-trained networks has 2 main components: feature extraction followed by fine-tuning. In the code, it's kind of all done at the same time. Within Keras, you actually have a lot of pre-trained models that already exist. You can also download model files, but typically these are good enough. You can see here there's a bunch of available models. The one we're going to be using today, I think, is VGG. Yeah, we're going to be using one called VGG19, which is meant to be for images. And as you can see, VGG19, I wonder if they have the information here. But yeah, it was pre-trained on ImageNet. And ImageNet is this gigantic image data set on pretty much every general object. I think there's a bunch of animals in there, a bunch of textures, so that different neurons have learned different things already.
Can I just interrupt you for a second?
Yeah.
So basically, these pre-trained networks to save you of that process of running a Jupyter itself for 17 hours or whatever.
Absolutely. Yeah, it definitely saves some of that time.
Okay.
Yep. So to demonstrate the utility of pre-trained network, we're going to compare the performance between a baseline and a model using a pre-trained network, I believe. I hope that we do that. Let me just double check. All right. Let's see. Okay, so let's see how it works. So from this, we're just going to use one of the ones that are built into Keras. called VGG19. And all you have to do is just instantiate that first part. So here, this is how we can instantiate VGG19. One thing that I did want to demonstrate is this include top part. So let's just take a look at this output. So this is the pre-trained with include top, and it's installing. And if I take a look at the summary, some of you might have already seen this in your networks, but basically this pre-trained network has all of these layers. It says your input layer, your convolutional layers, pooling layers. These we saw a bunch of, yeah, basically a bunch of convolutional and pooling layers. And then at the very end, you have your flattened layer, 2 dense layers, and then your prediction layer. So this, I believe, actually predicts it into one of 1,000 different classes. And for this purpose, we don't really need that part, right? Because we want this network to be able to classify our data, not its own data. So what we can do is we do include top equals false, which is interesting because technically this is the bottom, but I guess depending on which way you're looking at the network, it depends. So if I do include top equals to false, let's take a look at this summary. So with include top equals to false, it ends at the last pooling layer. So I think it's called block 5 pool. Block 5 pool here, that's where it ends. So basically this neural network with include top equals to false has all the neurons that have learned about, you know, different colors, textures, maybe like edges, shapes, stuff like that. It's hard to say what it's learned, but we can add further layers to take that information and classify it for whatever we need. Another thing to note, you can see that the number of parameters that there are in total is 20 million. So you can imagine how long this took to train. So really quickly, the way that you utilize a pre-trained network is actually pretty simple. Keras has it done all automatically for you. First, you start by instantiating a sequential model. And actually, let me pull up our original neural network so we can see. I think I call it, yeah. So just to compare it with our first regular neural network, which we started by instantiating it as a sequential model and start adding layers. In the same way, we're going to instantiate a sequential model, but we can add our pre-trained layers just like that. So I'm just doing cnn.add, and that automatically adds all of these layers. And I did overwrite this to be the one without the include top. So let's do this. We're just going to add the pre-trained layers. Something else that you have to do is, because you don't want those layers to be trained anymore, you can actually freeze those layers. And so per each layer, and this actually kind of works like object-oriented programming, if anyone remembers that, you can set all of the layers trainable parameter or trainable attribute to be equal to false. So just to show what this means, and actually let's just add these other layers as well. So I'm just going to add a flatten, 1 dense layer, and then our output layer just real quick. Oops. Hold on, let me make sure everything is, oh, sorry. I think I can just do this. This works. There we go. Oh, did I not import layers? Sorry about that. Okay.
You didn't import flatten, maybe. Is that the part of it?
Yeah, so I could import flatten, but I can also import all of layers.
Oh, I see it.
Yeah, so I just did that. There we go. And so for every layer, let's just see and verify that the right layers are frozen and we can still train the new layers that we've added. So to see this, you can see that all of our VGG19 layers are not trainable, because here we're printing layer.name and then layer.trainable. Our VGG19 layers are not trainable, and then all our new layers are. So what this means is that as we feed in new data, the only parameters that are going to be adjusted are the ones in these 2 layers here. And technically flatten as well, but flatten doesn't have much, you're not really training any parameters when you flatten. Any questions about putting a pre-trained model with your network? All right, well, after this, all you have to do is the same compile steps and the same compile and fit step. I actually don't have an example here, but I have also linked a, yeah, I've linked the walkthrough, I believe, not this one, but I believe the walkthrough in the last notebook has an example using this pre-trained network. So yeah, basically with this, after you compile your model should perform a lot better because it has already recognized, or it has neurons that can already recognize specific parts of an image. Cool. Any questions at this point? All right. So the next thing, and this study group is kind of like looking at different things with regards to neural networks. We're going to look at how we can do grid search on a neural network. So as we've learned that with our neural network, there are a lot of things that you can tune. Like even with this very simple one, you can tune like, you know, the number of nodes in your layer, the activation functions, maybe different loss functions, different optimizers. And it can be pretty complicated to just, you know, run a bunch of the same network just by adjusting one of these things at a time. So therefore we have grid search. There are two ways to do it. So the first way, you can actually implement the regular scikit-learn grid search. I've linked, this is actually a very, very straightforward article that talks about how you can do that, and all the code is there. So feel free to use that. I personally like this other method of using this other library called Talus. Well, the grid search method using scikit-learn's grid search, it just involves creating this model object such that scikit-learn's existing grid search will work on your neural net. So it just includes, you know, coercing your neural network into a data type that is recognized by scikit-learn. I like this because it was actually built for Keras. And this library lets you tune without having to create the model object. And also it outputs your combination scores into a CSV file, which I really like. So just really quick, I'm gonna set up, this is the same data that we used here. So the Pima Indians data set, very, very straightforward classification problem. So what I'm gonna do here that's new is import Talus to see how it works. So I'm gonna use this CSV. We can take a look at our training data. So we look at X-train, for example, we have all of this, and our Y-train is just a series of zeros and ones. So the one thing that's slightly different when you want to do a grid search, all you have to do is set up your model in a function. So here you can see all of these steps. We have our instantiation of our model, our layers. This is our output layer. So this is all pretty familiar to us. I'll talk about what these params things are in a little bit. But within this function, we also have our compile and we also have our fit. So this is all going to be in a single function. On top of that, think about what you want to tune. So for example, here I want to tune the number of nodes in my first dense layer. Anything that I want to tune, I'm going to make a new key in my params dictionary. So here's my params dictionary. I have my dropout and I want to tune my dropout as well. I have the number of nodes in my first layer, which I'll just call nodes 1. I want to try different optimizers and different activation functions. So for each individual thing you want to tune, all you have to do is call on your parameter dictionary and just call in the dictionary's values. So having my nodes 1 to point to a list of 12, 20, and 100 just means that here, where I'm using nodes 1, it's going to test 12, 20, and 100 in this position here. Same thing for the rest. So for example, I want to try different optimizers. I would just call on params optimizer here to try out both Atom and SGD as an optimizer. So actually, oh yeah.
Quick question. How did you come up with the figure of 12, 20, and 100?
Arbitrary. I just came up with the numbers to guess.
Okay, so yeah, I mean, is there any place where you need to specify these numbers?
So you specify them right here. So this is like when you set up your grid search, you know, when you're doing your like N estimators, for example, you set the you set them all up in a dictionary like this.
Okay.
Mm-hmm.
I guess another question, I guess it's basically a Python question. So what would that look like? You know, basically you're replacing nodes 1 with those 3 integers.
Mm-hmm.
But how would that look like if you write it out just like normally without, because I'm confused how it cycles through each one. There's no for loop or anything.
Yeah, so all of that is actually done in this Talus function.
Oh, I see. So that will cycle through it for you.
That's right.
Okay,
that's right. Yeah. So yeah, Pythonically, I'm not too sure how exactly it's doing it in the backend. I think it recognizes, like in your params dictionary, all of the combinations of all of these things. So yeah.
Okay, well, as long as the Talus does it for you, that makes sense to me then.
That's right. That's right. So let's just run these two really quickly. Oh no, what did I forget here? Oh, there we go. So after we set up, the function that builds our model every time, and our parameter dictionary, we use the talus.scan. One thing, I actually spent a lot of time debugging this. For some reason, you have to do with dot values. It doesn't take in the exact data frame for some reason, but doing dot values saves it from fixes it. You give it your params dictionary, and you give it the function that creates your model. Experiment name being grid, I'll show you all what that is for, but basically what Talus is really great for is it saves all of your results to a CSV, and this is what the folder for your results is going to be called. And I'll show you all what that looks like. So hopefully it doesn't take too long to run. Okay, maybe a little bit. But basically, while this is running, it goes into grid, and you can see that it is updating a CSV. So right now, I can actually show you this CSV was from before. I ran this a couple weeks ago, and these were all the results. It saves as a CSV. You can do pd.read CSV, and you have all your results there. You can sort them and all of that. You can also see this. It's actually currently running. You see seconds ago. Hopefully this will let me open it. Is this the right one? Yeah. So I think this is being updated as we go, but I don't want to mess with it as it's running. But yeah, this grid search is going to keep training and evaluating your model with every combination of parameters. And then you can actually pull out your best model. Hopefully this doesn't take too much longer. It looks like another 20 seconds. But yeah, after the fact, you can actually read your results as a CSV. Let me actually copy the name so we have it. And yeah, you can see 0216 because it's today's date. Let's do this. So, and right when this is done running, we should be able to read the CSV. All right. When this is running, there you can see that we have all of our results. I sorted it by validation accuracy right here. And we find that this is our best combination parameters using 10 epochs. This is our loss in accuracy using ReLU for both activations, 0.1 for dropout, and 100 nodes in that first layer, and with an SGD optimizer.
You didn't run the cell above it. What does that one do?
So this one just gives you your best model. So you can see this just gives you a sequential model. This is like, when you're doing a grid search and you can get your best estimator, you can do it this way. I actually prefer that you can do this and you can technically use the model, but there has proven to be some issues if you just use the model out of this. So if you were to do like model equals to this, and when you try and do model.predict, it doesn't always work. So I actually do recommend that after you've done your grid search, just re-instantiate a complete model on its own. I actually do that in this next step. So I'm just going to use all of these parameters, and I set up my model again here. But yeah, here's another Talus walkthrough if you want to see like how the code is set up. But yeah, before I move on, questions on using Talus or grid search for your neural network? All right. Okay, so now we're going to talk about saving your model, which is really, really quick. So here we have our model. This is the same one that we had before that we already trained. And I just put in not already trained, but we've already found out what our best parameters are. So I put all of those best parameters in there. I run the model real quick. It is all done. Just for the sake of seeing it, let's see our loss and accuracy numbers. Oh, it has to go 200 epochs this time. All right. So this, you can see that these are what our results look like. I mean, our loss has gotten down and started to plateau out. Our training accuracy and testing accuracy down to up and sort of has started to plateau out as well. To save your model, it's two really quick lines that are surprisingly hard to find on the internet, but you save your model and you also want to save all of your weights, your parameters. You can do this same code if you use Pretrained Network as well. So all you have to do is save your model, and just by default, it has an extension of H5. I'm not too sure what the origins of that is either, but you save your model and you save its weights. You always have to do these two steps to save the model, because if you don't save the weights, you'll just have the layers without its trained parameters, which defeats the purpose. So I've saved both, and then we can load up the model, and I'm going to save it as different variables, just so we can see that it is reloading our model. Oh, and by the way, we can see that our model was saved here. We have our model weights and model, both from seconds ago. And then with this, let's load our models back in, and I can, just to show that we can use the same model, we're just going to evaluate our test set, and we get an accuracy of 0.67, which should be similar to the final accuracy down here of, yeah, 0.67. Any questions about saving the model?
Could you point out where is that model on the line graph? Like where would it plateau at? Where does the model say like?
You mean like?
Yeah, like there. Like, yeah, so because how many epochs? So it's under 200 epochs. Obviously, that's too far because it's basically not gaining anything. So where does that model say that it's done?
So this model, I didn't do any like early stopping. I didn't tell it to stop or whatever. So it actually is all the way at the end. But if you had introduced something like early stopping, technically it wouldn't keep training. So you actually wouldn't have these values. So this model would maybe like cut off. Let's see. One way you can do it is look at where your test accuracy goes down by several number of epochs in a row. So let's see, maybe like around here, this like constant down looks like it's going down for a few epochs at a time. It might stop there.
Okay.
Yeah, just as an example. I don't think that, yeah, it's pretty hard to see from here, but yeah. Cool. Anything else about anything we've talked about so far? Because the next is going to be pretty conceptual, but could be helpful for those of you who are thinking of doing more like time series capstones, and you want to try something other than a traditional time series model. All right, so we're going to talk about recurrent neural networks. I've linked these 3 walkthroughs because I don't have much implementation code, but all the code here, these are examples that other students have used and they like, so feel free to take that from there. But I do want to talk a little bit about the theory of a recurrent neural network and how it works. So let's start with this slideshow. All right. So recurrent neural networks. And again, for context, this is actually material from another instructor that I'm using. Recurrent neural networks has never really been part of the curriculum, but a lot of students tend to try it out, especially if they're doing something more time series related. So like something like stock prediction or any sort of forecasting that, you know, is not getting accurate results with a traditional time series model. Sometimes they just try and implement a recurrent neural network to see if it works much better or not. So with recurrent neural networks, we have to think about sequence learning. The whole idea of it being recurrent is that the order of things matters, which is why forecasting makes sense, right? Like if you have the stock price from 10 years ago and you want to find out the prices for the upcoming month, the order in which the prices happened over the past 10 years does matter. So with sequence learning, you're not just talking about collection of items, but also an order. So ABC will produce a different outcome from ACB. So things to consider: how can each element be represented? Again, it always has to be numerical if you're feeding it into a network, or is it some sort of vector? You probably won't be dealing with this, but there's multivariate time series where you're trying to predict multiple things concurrently at once. And then you could think about a vector. An example is, let's say you wanted to predict the price of like the S&P 500, maybe like 10-year treasuries, and I don't know, something else all at the same time. You'd have vectors of 3 coming as a sequence. Oh, or maybe in the time series project that you all have, you have all of these zip codes. Maybe you want to take like 10 of the zip codes and predict all of them at once. You would have vectors of 10. I say this, but I am not expecting any of you all to be doing this for your project or even for the capstone, because it's pretty hard to implement.
Yes, can I ask a question?
Yeah, for sure.
I'm actually running while I'm listening to the class. So
Hey, Marv, I can't hear you.
or whatever the case might be. So if I wanted to match up the most frequent words that you ever use in Twitter at a particular time with, like, say, stock price, historical data, would that be a situation that you're like? Is that an example of what you're talking about?
Oh, okay, I see. So like you want to use, so let's say, I think the most common example right now is Tesla. So let's say like if a lot of people are talking about Tesla, you would correlate the volume of people tweeting about Tesla with the stock price. In that scenario, I would say actually using a recurrent network, an RNN would be a little bit of overkill, just because you can, if you're saying that two are correlated, something like a linear regression might make more sense. Just so you say like, all right, if I don't know, 10 times more people are tweeting about Tesla stock, there is some sort of, there's maybe like 10 times more, I don't know, 10% price increase in Tesla stock. That's more of like a linear regression problem. Recurrent neural network is sort of like if you want to forecast, or in that example, with multivariate time series, if you want to forecast multiple things at the same time. So that would be more like if I want to forecast people talking about COVID and people talking about wearing masks and people talking about, I don't know, vaccines all at the same time. If I want to try and forecast how many people will be tweeting about all of these 3 topics at the same time on Twitter, that would be a more appropriate use of RNNs.
Gotcha. So then in that case, now I understand. So then in that case, would you use NLP? Like if you want to do that whole thing, would you use NLP plus time series plus RNN?
Yeah. RNN is actually another common use case. I have a slide with like use cases, but another very common use case of RNNs is actually for text prediction. So I'll talk about that in a little bit too.
Awesome. Okay, thank you.
You're welcome.
Ish, I have a question. So now let's say now we are using this for the time series, like with project of the Zillow zip code. So we have picked up one zip code and then there is a sequence, right? I mean, there is an order which is right on monthly basis, which is there. Now, what happens when at certain points, right, where the null value has been replaced by 0 as the price, right? But then, right, it is a number. In any case, it's a number which has been filled, right? And when the prediction comes, would it consider it as a 0, or it will consider multiple parameters to predict?
Usually if you fill something with 0 or some sort of placeholder, your model doesn't know that it is a placeholder. So this is more in terms of like your data cleaning and data preparation. You should fill in your null values with something that makes more sense. So if you fill your null values with 0, it will throw off your model.
Yeah, that's one reason I was asking, because like when we fill in with null, anything with the null values, we need to be very sure like what exactly we are filling in.
That's right. Yeah, that's right. So I would say that for time series, actually, I think one of the most common methods of filling in your null values, I think you saw like forward fill, backward fill. Sometimes you can even like take like a I forget what that's called. Interpolating, extrapolating. I forget which direction, but basically if you have like price is 1 on one day, 3 in a day after, that middle day would be 2. So yeah, it is very important to consider how you're filling in your null values. I think especially with time series, because if you fill your null values with something completely random or as a placeholder, something as a placeholder, your model will see it as a shock and it might take that into consideration.
But then you could, thank you for saying that, Yish, but then couldn't you kind of double check that by doing the line graph or the dot graph thing?
Well, for time series, most likely a line graph. You just want to make sure that there's no like weird data going on. Again, it is very dependent on context, like, you know, market crash happens, for example, right. That's normal. But yeah, you want to verify that there are no data points that don't make sense.
For sure, okay.
All right, let's move on. So a very common example of sequence learning is actually something that we've talked about, word embeddings. In this diagram over here, it's kind of how word embeddings are trained. So remember I talked about how word embeddings are trained. Let's say you want to try and learn the meaning of the word coffee. You're going to look for a body of text that uses the word coffee a bunch, and it's going to learn the meaning of the word coffee based on, for example, the 5 words that come before and the 5 words that come after the word coffee. And then this is done. And as you know, with neural networks, the parameters are kind of like meaningless, like the weights, it's very hard to attribute like meaning of the weights, but that's really what's being done. How word embeddings are being trained is you're feeding in all the occurrences of words around the word coffee, and you come up with some sort of word embedding based on inputs into your neural network. If that didn't really make sense, that's okay for now, honestly. So out of sequence learning, some common use cases of sequence learning is frequent pattern mining. And frequent pattern mining is actually similar to looking for common occurrences of the same thing, right? Patterns that happen frequently. So actually one usage of frequent pattern mining that we talked about before was looking for n-grams. So FPM, n-gram is a type of frequent pattern. Looking for n-grams is a kind of frequent pattern mining. Of course, there are much more complicated examples. Like for example, you know, you want to look for every occurrence of like a minor market crash, maybe. That would be another example of frequent pattern mining, and you can use a neural network to try and look and locate these occurrences using something similar to a sliding window. So you imagine you have a sliding window of like, I don't know, maybe like 10 days, and you like just look across, I don't know, the entire history of the stock market. You can look for these occurrences of, you know, I don't know, minor market crashes. Sequence learning is a very, very broad term. So within sequence learning, you actually have ARIMA and its variants, all the time series models that we had talked about before, and Markov models. We actually never talked about Markov models, but it is, I believe, in your appendix of mod 2. Markov models are basically forecasting using theory of probability. So for example, actually one very common usage of this is in music. So if you have like the notes like ABC, for example, based on the past occurrences of ABC and what notes usually come after that sequence, Markov models will come up with some sort of probability and figure out what the next note should be. Text prediction also can use Markov models.
So, I mean, does that mean that like that the AI would probably be able to sing?
Oh yeah, there's a lot of AI creative music. If you actually look up on YouTube, there's like, there's a pretty famous AI symphony. I forget the name of it off the top of my head, but there is a lot of AI creative music.
Wow, cool.
Yeah. But yeah, these are just one of a few of many, many examples of sequence learning. All right, so let's talk about why a multi-layer perceptron isn't enough. So just to recap, a multi-layer perceptron is basically all of the neural networks that we've been talking about so far. So this is what a multi-layer perceptron is, and why isn't it enough? Any thoughts? Yeah, I wouldn't expect anyone to have any thoughts about this, but anyways, let's move on. So the one unique thing about recurrent neural networks versus an MLP is the fact that your input data goes backwards. So regular forward feed neural networks, like this one on the right here, have an activation function that's fed all the inputs and then goes on to the outputs. So pretty normal, your data just goes in one direction. So recurrent neural networks use a recurrent activation that's also forward propagated. So this arrow that loops back, you're basically taking into account, all right, I'm making this prediction for tomorrow. Tomorrow I have the actual price of tomorrow. I take a look at the error and I take that into consideration before I make the prediction for the day after. That's a very, very simplified explanation of what this is doing, but you're basically taking into account your error as you move forward with forecasting.
So it basically just, it better models the way a human being would think.
Yeah, kind of.
Well, maybe not everybody, but I mean, just,
yeah,
I just mean like it just, before it learns from what happened before it does another prediction.
That's right. It has memory of everything that has happened. And a subset of recurrent neural networks that will come, I think, in a couple slides is LSTMs, long short-term memory, which some of you who have been doing additional research on time series, you more likely will use the LSTM subset of recurrent neural networks. I'll talk about that in a little bit too. But yeah, the main structural difference between a multi-layer perceptron versus a recurrent neural network is this fact that it loops back around and it takes into consideration the mistakes that it's made and goes back and then makes future predictions based on that. Yeah.
Quick question, Yish. So is there, I feel like with the RNN, I'm thinking to myself, well, is there a time where I wouldn't use it? But like, is there a time where you would use feed, just the regular forward feed, and you said, well, actually, we don't want to use recurrent?
Mm-hmm. I think you can really decide what neural network you want to use based on the task at hand. So recurrent neural network is anything that has to do with forecasting. If you're only predicting things that happen in the future, so time series, we're always forecasting, or text prediction, because you're making your outputs will be based on what happens before. So in those situations, those usually call for a recurrent neural network. There have been instances of recommendation systems using recurrent neural networks, most commonly in actually like song recommendation systems, where there have been like new theories that people are thinking about where people want to hear songs in a specific order and are trying to take those things into account. So yeah, in that case, again, order matters. The fact that you want to care about the sequence of things that are upcoming, that's usually key to identify when you want to use a recurrent neural network.
I also have a question about the recurrent neural networks. So, when it loops back in, do we decide when is a good stopping point? Like when is the loss, I guess, small enough to where there's no point of looping back in? Or is that something that it does on its own?
The looping back in is something it does on its own. And the looping back in is just so that it can make future predictions. So if you stop that looping back in, so let's say I don't know how to explain this. Basically, yeah, it does it on its own. I personally haven't implemented too many to answer that confidently, but I haven't played with the fact that I haven't played around with stopping it from doing that. I imagine you can definitely play around with that, but off the top of my head, I can't see why I would.
All right, thank you.
Mm-hmm. All right, moving on. This is just a diagram to show that recurrent neural networks can exist in different forms with inputs and outputs. So the way that you read recurrent neural networks, and if you were to take a class on recurrent neural networks, they will get you used to reading this kind of diagram versus the one with the nodes. So the way that you read this, inputs are the red, all of those intermediate layers are the green, and outputs are the blue. So this just goes to show that recurrent neural networks can be used for different cardinality of inputs and outputs. So it just means that inputs, you can have single inputs, like for example, I don't know, like text prediction. If you just want to predict the next word, an input of one word is enough. If you want to do one-to-many, one word, you want to predict the rest of the sentence, that would be an example. Many to one with like a sentence, you want to see what the end of the sentence looks like, stuff like that. So this just goes to show that your recurrent neural networks can take on different inputs and outputs, and you're not always constricted to, you know, just a single variable going in and a single variable coming out. I will say that I have only personally worked with one-to-one neural networks, recurrent neural networks, just because those are the ones for like stock predictions, anything that you're doing like a single variable. The rest I personally have not had experience implementing. Also, I can't really think of too many instances where I would want to do this. But yeah. All right, so let's talk about some more concrete examples of when you use recurrent networks, neural networks. So within NLP, predictive text and sentiment analysis. So predictive text, as I mentioned, you know, you can input a series of words and it'll help you figure out what the next words will be. It's recurrent neural network because based on what, you know, prediction one, let's say the first word that you're having it guess, based on that, it's going to take that into account to predict the second word. So that's where the recurrence comes in.
So that's like when you're texting somebody and the options come up, or like but I say a Gmail on my phone,
yeah,
it often says like, I'll meet you, and I'll say at the coffee shop, and it'll offer me a suggestion. That's what it's doing.
Yeah, that's right.
Okay.
Yeah. I don't know if they're exactly using this or something using something way more advanced, but something like that can be built with a recurrent neural network. I have had a couple students do capstones that do predictive text, so I will send those out during the capstone time. You can also use it to do sentiment analysis or pretty much any word embedding. So we talked about that already. Next, recommendation systems. With RNNs, as I mentioned before, if you care about the order in which something is recommended to you, or like a set of things is recommended to you, and RNN is an easy application, not easy, but it's you would think that RNNs are something that you can use to do that. Content filtering as well, but although it's not a very common use of RNN, so I personally haven't seen any examples of that. Next, as I talked about, time series forecasting, audio interpretation. This is actually pretty cool because you can use a combination of RNNs and CNNs to analyze waveforms of like audio, which is pretty interesting. I think Spotify is actually working on something very, very similar. But yeah, you can also do recurrent CNNs, which is crazy, but that basically allows you to analyze videos and how, you know, frames are changing. Yeah, with every frame, like the order of pixels change, you can do that. I've never implemented that. I imagine it would be very, very computationally heavy. But theoretically, that's what you would use to do that. All right, I'm gonna skip the next couple of slides because these talk about, basically the prerequisite to this is watching a few videos that I will link out to you all later. But yeah, I'll skip all of these mathy slides. And then I'll talk about Lstns. So Lstns, as I mentioned, is the more nuanced subset of RNNs that I think most of us will end up using if we want to do something like this for our capstone. So with LSTMs basically stand for long short-term memory. So RNNs basically are not super good at remembering things. It's not good at figuring out what is important to remember about the past, if that makes sense. This idea of long short-term memory, it also trains your neural network to recognize what parts of the data it's already seen is relevant to making forecasts in the future. So for example, if you're thinking about, let's talk about maybe in time series, for example. We had that like market crash in 2008. Is that market crash in 2008 very relevant to predicting housing prices over the 5 years after that? Some ways no, some ways yes, right? Yes, it's important because you know that all the prices are going to start lower, but in some ways no, because a market crash like that is unlikely to happen in, I guess, the next 5 years. Not a very concrete example, but basically the fact is that an LSTM will allow you to, will allow your network to learn what things are relevant for making predictions. So this example talks about how LSTMs could be useful in predictive text. So the sentence that we have here, there was a castle in the mountains on a river across from the valley where the king's army was marching. So from this, an RNN would actually find that king's army, these two words are going to be related to each other and also important because they're right next to each other. Army and marching is just separated by was, which can be argued is a stop word. So coming up with these predictions from kings onward is going to be fairly easy for a regular RNN. However, this sentence started with the word castle. So the castle to king connection for a regular RNN might not be something that it picks up on because it's separated by so many other words. So the model might have forgotten. Again, because of the black box, it's hard to say whether it does or doesn't. But in an RNN, it's more likely that it has forgotten the connection between castle and king just because of all the words that separate castle and king. So an LSTM sort of solves that problem because it takes into account, or it is also constantly thinking about what are words that I think are going to be important for predicting the rest of this sentence. So in a regular RNN, if I start this sentence this way, it is a lot less likely that so far down the line, it's still going to be talking about like the king's army was marching. Does that make sense? All right, and oh.
So is there any way when we are actually coding it, we specify that, okay, the memory needs to be for the past 5 words or past 10 words kind of?
Yeah, there's no way to, I guess you could if you want to code your own like activation functions, but actually the next I'm going to talk about will sort of explain on a high level how your model is deciding what things to remember and what things to forget. There's actually a component of an LSTM that is an add-on from RNNs to basically learn these things.
Okay.
Right, so here's the example. The thing that's missing is a forget gate. So the forget gate is basically a part of an LSTM that tells the neural network, what should I remember, what should I forget? And that's something that has its own set of parameters, and it's trained, it's updated with backpropagation with a bunch of training examples. So yeah, this forget gate will basically tell you what to keep or throw away. All of these other components are actually pretty similar to regular RNNs, but this forget gate is the main thing here. Having this forget gate, basically, as you train it, it learns, all right, what words are words that I should remember? Maybe things like proper nouns, maybe things like, I don't know, I guess other nouns, and words that commonly have other things associated with it down the line, stuff like that. So yeah, whatever your input data is, your model will also learn whether it remembers or forgets that. And not only just that, but also in some way, like how long should it retain a thing in memory versus, yeah, how long or short it should retain one of your inputs in memory. But yeah, everything is all learned in backpropagation. So you actually don't have to tune this individually. All right, that's, I think, all I had to share. The last slide I had was all of these resources. But yeah, does anyone have any overview questions? I will say most of like what I talked about with RNNs just went over your head. That's completely fine. I will say even for the people who use this in their capstones, it's it takes a long time to get into the theory of neural networks, as I've talked about over the past couple of weeks. So you can definitely implement it if you want, but just be careful that, I don't know, it is still possible that someone might ask you this in an interview, so with caution. All right, any questions to close out?
not related to this, but I am actually trying to create a data frame out of all the the Dickey-Fuller tests, right? So is there any specific way which it can be done? Like, let's say I have 5 zip codes for which I have run Dickey-Fuller tests. Now I want to club them together and create a data frame of the results.
Yeah, so your Dickey-Fuller test outputs a dictionary. I don't know if you remember that. But your Dickey-Fuller outputs a dictionary. So for each zip code, you can honestly just update the dictionary to include a key with your zip code. And then when you put it into a dictionary, you'll have all the information. So when you put all of your data frames into it, when you put all of your dictionaries into a data frame, you'll have it all there.
Okay, let me just, can I share the screen?
I'm gonna stop the recording first and then we can talk about it.
Okay.
Yeah, but before we move on to that, does anyone have any questions related to this? All right, I'll stop this recording real quick.